Hey, it's Tony from Adafruit, and welcome back to Watch Tony D's Desk. So it took about a month break or so from the holidays and then just getting over a cold and some sickness. But anyways, we're back with a new year and all kinds of excellent, awesome new content. And one thing we're going to focus on a lot this year, and even last year we saw a lot of focus, is Micropython. And in this video, I want to talk about something really cool. So this is a new derivative of Micropython from Adafruit called CircuitPython. And this is a beta release that we just put out this week of a version of Micropython that can run on Adafruit's educational boards. So this will be really exciting. It's something we've been working on. We've already got like a beta port to some of the processors that we've been using that's been released. And so this is an evolution of that. And in this video, I just wanted to go through some of the highlights of what CircuitPython is and maybe why it's interesting and what you can see more of in the future as we continue forward and eventually get a good release out for this. Because right now, again, this is kind of beta, it's early access. Early access in the sense of it's early code, so things are going to be a little sometimes unstable, and things are evolving too, so we're changing it. But, you know, we want to move fast and push things out and get feedback from people and see how things work. So the big question though that you might have is, okay, why CircuitPython? What about Micropython? Like, what are they? Are they the same thing? Are they different? Is one better than the other? And they're actually very similar. So Micropython is the version of Python that runs on little microcontrollers. I've done tons of videos on those, and in fact, I'll put a link in the description below when this goes up on YouTube so you can check out a whole category of Learn System guides that we have on using Micropython. Excellent open source version of Python. It's a re-implementation of Python that runs on memory-constrained microcontrollers like some of these powerful chips like the ESP8266. It doesn't run on your Arduino Uno, but some of the other Arduinos like the Arduino Zero it might run on in the future. Anyways, though, so we've taken some of these chips like the Arduino Zero that you can use on some of these boards. Let's see, I think I have an example here. Well, we'll come back to what this one is, but this Magic Purple board is similar to an Arduino Zero. It has the same processor, and we've ported Micropython to run on that chip. Now, the interesting thing about Micropython is it's an excellent version of Python. It supports pretty much the whole core Python language, and it gives you really low-level access to your hardware. So the shining example of Micropython is this board right here, which I've talked a little bit about. This is the Pi board, which is a very fast processor. It's a Cortex M4, if I remember correctly. Much more speed than your typical Arduino. Lots of peripherals. This can do all kinds of fancy stuff like DMA access to to talk to your peripherals at high speed, and it has a digital to analog converter, and almost anything you can imagine this powerful chip can do. And one of the big focuses with Micropython has been exposing all of that functionality so that if you want to build some cool device that drives your LCD display at a really high refresh rate and you're being very fast and efficient, it's possible to do that with Micropython now. But you have to be a little bit more of an experienced user because you need to understand, what are the peripherals on this chip and what is DMA and how do you use that stuff and when does it make sense to use it, and even just using some of that adds some complexity. Whereas when you use a board like this one, and we'll come back to why this is a Magic Purple board. So this, if you've seen Circuit Playground, this is a special version that we'll come back to in a second. But this is basically a learning platform. So it has Neopixels soldered onto it. There's similar kind of brain as a certain type of Arduino on there. There's some buttons. You can use the edges to like hook alligator clips onto here for inputs and outputs. There's capacitive touch on here also. So it's a great little board that you can plug it in and get started. And so we have a version of this in the shop already. It's been super popular, and you can just program it with Arduino IDE. But anyways, a board like that is great for a beginner because you don't need to know, okay, here's how I connect up these peripherals, here's how I solder things together. You just plug it in and get started. The tricky thing though is, how do you make the software experience as easy or a little bit easier for a beginner compared to using something like Micropython that's giving you the really low-level granular access to the hardware? And so that's one of the things we want to do with CircuitPython is look at for Adafruit's boards that will eventually ship CircuitPython. How can we make it a little bit simpler and more beginner focused? And so that's one of the big differences between CircuitPython and Micropython. So CircuitPython is based on Micropython. It's a fork of it, a derivative of the source code. It's tracking the upstream Micropython, and we're going to keep it up to date. As new releases of Micropython come out, we'll pull those in and keep CircuitPython up to date. But the big difference is that it's focusing more on making it simpler for beginners. And so we'll make different trade-offs where the APIs might want to be simpler for beginners. So you might not need to understand, okay, what are the DMA and the timer channels and how to configure all these peripherals when you just want to talk to a device, maybe play a sound file on the speaker, for example. So look for more of that in the future with CircuitPython, but that's kind of one of the main reasons for it. The other reason is that we're going to support CircuitPython on multiple different boards that Adafruit sells. So for example, like I was mentioning, there's this Circuit Playground board, and this is a special Circuit Playground that you might have seen on Desk of Lady Ada. This one has a SAMD21 microprocessor, same as the Arduino Uno, or Arduino Zero rather. I was going to say Zuno, that would be an interesting Arduino. The Arduino Zero, which is the SAMD21 Atmel processor, we've done a bunch of videos about this one because we've been working on this port of Micropython and now CircuitPython to it. But anyways, this is one of the boards that we'll have. You might have seen this on Desk of Lady Ada also. This is a Gemma, which is the tiny little wearable platform, but this is a special Gemma, not because it's purple, but because it has a SAMD21 processor also. So that means this little board can run Micropython or CircuitPython specifically. So this will be really cool. You can, do a Python wearable or just a tiny little Python powered device. And there's a Trinket version also in the works for that. And then like I showed before, here's a Metro board. This is a SAMD21 processor. Really nice because it's Arduino form factor, so you can plug your shields and things into this. But there are other boards too. So for example, this one, this is the ESP8266 Feather Huzzah. So it's the popular ESP8266 Wi-Fi microcontroller. And again, this is another board you can get in the Feather form factor, and you can plug in all kinds of things like, here's a little LED matrix display that just plugs into that. So you have all these different types of boards, like the ESP8266 Feather, SAMD21 based boards, like the Circuit Playground board. I'm always going to confuse that one. The CircuitPython Circuit Playground. Boy, that's going to be a mouthful to say. But so you have boards like that have these multiple processors, and you've got all these cool gadgets and accessories that Adafruit has, things like, these little different displays and sensors. But you want to be able to use those on all of those boards. And so that means that each of the boards needs to have a consistent way to talk to peripherals. So if you're running code on this little Circuit Playground that's running your SAMD21 microprocessor, you want to use that same code if you're talking to a little display that you've wired up to this device. Ideally, you could use that same code with your ESP8266. So you'd wire up your little LCD display, maybe it's an I2C display like an OLED or something like that. You wire it up the same way, and ideally you use the same code because the API is the same. And the API is basically the programming code that you use to talk to the peripherals. And right now in the Micropython world, it's getting better in that the boards are slowly moving towards a more uniform model, but it's not as smooth as we need to support all of our boards. So that's another reason why we're doing a version called CircuitPython, is that we're changing the API to be simpler, like I said before, for beginners, but then also to be uniform across our boards, so that the code you run on an ESP8266 that's running CircuitPython will also ideally run pretty much without modification on other boards, like maybe your Circuit Playground, or maybe ideally, probably if you're going from a Feather, maybe a Metro or something like that. Or there are also Feather versions of the SAMD21 processor. But that's kind of the big goal, is that you'll be able to take that code, and because the API is the same or very, very similar across the boards, and there are sometimes small differences, like the ESP8266, it doesn't have hardware I2C support. It's based in software bit banging. So there's some small little differences, which you sometimes need to know about when you're using that hardware. But anyways, because the API will be the same, your code will be the same to run across those devices. And so it gives us a little more control by taking the Micropython code and changing the API to be uniform. We can make sure that it works across all of the boards and the devices that we have here. And we're also, not to say that we're trying to drop support for the upstream Micropython API. So for example, on the ESP8266, it's a really powerful chip. It has a lot of memory. You can store a lot of programs. The firmware for this can be really large. And so actually on CircuitPython for the ESP8266, it still supports the upstream MicroPython API. So the drivers that we've already written that let you control pretty much all of the feathers that we have, all the feather wings, the accessories you can plug into your feather. There's a driver for it now with MicroPython. You can use those on ESP8266 because we still have the old API there, and we have in addition the new CircuitPython API. But for some of these other boards like the Circuit Playground, anything with the SAMD21 microprocessor, that's a much smaller chip compared to the ESP8266, less memory in particular, and so the firmware, the MicroPython code itself, can't be as large, and so you have to make some trade-offs, and so we can't support both APIs. So we're basically saying let's use the CircuitPython API because that's going to be the beginner-focused one that we'll use here. So you'll see a little bit more about this in the future, especially as the API evolves. Like I said, this is the beta version. Nothing is set in stone forever, but we do want to explore how we can make the API simpler and how we can make it work across all these boards. Okay, so a lot of talking, and let's kind of get into some interesting things. Basically, I want to show a few demos that highlight some of these reasons for why CircuitPython is a cool new version of MicroPython and why we're going to be using it with a lot of our boards. So let's jump into the main view real quick. Let's see, we'll swap this up. It's been about a month since I've done a broadcast here, so hopefully everything goes smoothly. We'll see how things go. Okay, so yeah, here's the main view. And this is, I'll put links, by the way, down in the description, so when this is up on YouTube, you can go and check it out. This is the blog post that kind of announced earlier this week, the beta version of this. And so this is a really nice little write-up that Scott did, and Scott Shawcraft, he's been basically the main developer of CircuitPython, so all of this awesome work is kudos to Scott for that. And these are some cool little potential logos that we might have here. This is Blinka, the Python, so you'll probably see more about her in the future. And so this is just describing, what is CircuitPython, and it gives some links to where you can get the beta release of it, talks a little bit about some of the hardware and the API differences in particular. So definitely check out this blog post to get a quick little overview, and keep an eye on the blog in general because that's where we'll release, when there's a new version, we'll put a blog post out. And like I said before, I'll keep reiterating it. This is beta, so not everything has been updated yet. It's going to be probably a rolling release in some ways, in that it'll probably be at least another couple weeks or so for a lot of the drivers and guides and things to be updated. But again, like I mentioned, and you can see the hardware up here in the corner, these are some of the kind of don't ask it's not out yet versions of the CircuitPython. Eventually these will be CircuitPython powered boards, so Circuit Playground, Gemma, and a Metro board right here. But eventually, once we start releasing these in the shop, that'll probably be around the time that we start saying this is the official release of it, and so we'll have a lot more info and guides on how to get started for it. So for now, it's kind of, I don't want to say hackers only, but this is not as polished as some of the other things that you might have used for now, because it's still being created, it's still in development here. Anyways, the big thing that you'll want to check out here is this link to this awesome documentation that, again, Scott put together really awesome docs here. So there's a great documentation site, and let me actually go back up to the main page here. This is the CircuitPython API reference. So this is great to check out if you're getting started with CircuitPython and you want to understand how the APIs have changed a little bit on here. And so it talks about, for each of the high-level modules, what are the different functions and classes and things inside of there. So you'll see one big difference in the MicroPython upstream API. All of your machine access is through a module called machine. So you import machine, and that gives you, like I was showing before, here's the Pi board, that gives you all of that really low-level access to every peripheral on this device. Whereas in CircuitPython, we've kind of changed things up a little bit because, we didn't want to use the same name, machine, because that would be a little bit confusing, and also why we didn't want to use the same name of MicroPython. I mean, we could have said this is Adafruit MicroPython, and actually we called it that for a little while. But we don't want to have any confusion, because if you have code that you've written for CircuitPython and it uses this API, and then you try and run it on a board that uses MicroPython upstream, it's obviously not going to work because the APIs are different. But it would be really confusing if it was, if you saw this as Adafruit MicroPython and isn't it the same? No, it's different. So that's why the naming is different, and also why some of these modules have a different name. So, for example, if you take code that's written for a MicroPython board that uses the machine API and you try to use it on a CircuitPython board that doesn't have the machine API support, so the ESP ESP8266 would have the machine API and potentially work, but for some of these boards with the smaller processors like the SAMD, you try to run that code, it will fail. It'll say, oh, I don't have the machine API, like import machine fails. So watch out for that if you're using it and you get that error. It basically means that you're trying to use code that's not written for this board, and so that's because the modules are different. And we didn't want to use the same machine module name because even within the module, the support is slightly different in how you do things like access digital I/O or talk to your SPI or I2C peripherals. So just using that same name might make things even worse, because now your code, the import statement would work, but then later on when you try and use your device, things will start failing. So it's a little bit better to just fail early and hopefully catch the error and realize, oh yeah, I'm not using the right code for this board. But anyways, check out the documentation here. It goes into really nice detail about the basics of what you can do. And again, CircuitPython, it's based on upstream Micropython. Really just think of it as adding features to Micropython. We're not like taking away core language features. The Python language itself is the same, and we really don't want to touch that as much as possible because Micropython and Damien George and the folks that have developed Micropython have done an awesome job of porting Python. Pretty much the whole language is there. So we're just really taking that core language and adding slightly different APIs to it. So the core language is all the same. And the API differences you can see here. Right now, the basic support for digital I/O, analog I/O, talking to SPI peripherals, I2C peripherals, even serial peripherals, I believe, is in there right now. So that basic support is there. And then some of the other peripherals and things are going to come later. So some of these boards have things like digital analog converters or analog to digital converters. Well, actually, that support is there. So, but you'll see there'll be more things that come eventually for this. For these boards. Okay, and so then the high-level modules, I'll just mention real briefly. The one module that you probably want to check out is this one called native I/O. It's called hardware accelerated behavior. Basically, this is access to the native peripherals on your microcontroller. So things like the analog to digital converter that's on that chip, or your digital inputs and outputs that are on the chip. All of the stuff that was in the machine API previously or in upstream Micropython is basically in native I/O. So that's where you want to look. If you're thinking, okay, where is digital inputs and outputs? It's in native I/O typically. Now, the interesting thing is there's a version called bitbang I/O. And so this actually has a bitbang or a software implementation of the I2C and SPI protocols. And it has the exact same interface as native I/O. So the nice thing is you can swap between if you need to use maybe a software SPI to talk to a little TFT LCD that you hooked up to some digital input lines. Without changing all the driver code or changing all of your example code, you just change which module you import, and then your code will be pretty much the same, but you're using a software interface or like a bitbanged interface to that device. So hopefully it'll be really easy to swap between those by keeping those interfaces the same. But that's what the bitbang I/O module is for. And then the board module is kind of an interesting one. So this is one, there's not a lot of documentation for this. I'll show more an example of what this, what's interesting about this. But basically, again, like we said, we want to make this a little bit easier for beginners. So on a lot of the Micropython boards, you kind of have to know what are the pins on your board, and you have to address them sometimes by, on some boards it's a string, on some boards it's a number that you address them by. Sometimes that number is the board GPIO numbers. Sometimes it's a physical pin number, like on the Raspberry Pi, for example, it has all different types of layouts of the pins. That's really confusing and can be kind of problematic, especially for beginners. So the board module basically has a pin instances as high-level objects, and I'll show you why that's interesting and why it kind of makes sense to do something like that. In a moment here, we'll look at an example. And then there's a little bit more good info about what are the supported ports. For how to load this onto your board, check out the previous guides I've done. I'll put links in the description when this is on YouTube. There's a guide on how to load on the ESP8266 Micropython and how to load on the SAMD21 Micropython. So this CircuitPython firmware, you load it exactly the same way. In fact, you download this .bin file, which is your firmware binary file. And that's exactly like the binaries you get from micropython.org or if you build them yourself. So the process is exactly the same. You're just choosing which firmware you want to use. for these boards. And it also may be good to call out too, in that this doesn't change your board in any crazy way. You can load upstream Micropython if you want, and then you can swap to CircuitPython. You can go in between both those versions, so it's not going to change anything at a hardware level. Okay, so let's go and let's actually do a quick little demo here. So I'm going to start with the Circuit Playground board. So this, again, like I said, this is a version of Circuit Playground, which is the all-in-one electronics board, but this has the SAMD21 microprocessor right in the side right there, this big chip right here. And so this is cool because so we have CircuitPython or Circuit Playground today. That's a board you can actually buy in the shop. But the Circuit Playground we have today is using the AVR, the ATmega32U4. So it's a much less powerful chip. It has, I think, like only a quarter of the memory, flash memory if I remember correctly, and even less RAM. So it's, you can't do as much on that chip. So this is cool in that it's going to be a more powerful version, but it has the same peripherals. So like I said, it has Neopixels, it has a sound sensor, or a microphone rather. It has a little buzzer or speaker, really. And that's actually connected to the digital analog converter that's on this better processor. So you might in the future see actual audio outputs, like playing a WAV file potentially, but more on that later. It has some buttons on here, so little push buttons. There's a slide switch. You can use capacitive touch for all of these little outer pins. You can hook alligator clips up to them, use them as digital inputs and outputs. Lots of fun stuff on this board. Anyways, let's plug it in, and this is already loaded with the latest version of the CircuitPython firmware, and so it boots up, and I'm going to show you something cool. So again, this is coming back to one of the big reasons why we like CircuitPython and why we're creating CircuitPython to be easier for beginners. And so one of the things that's tricky for beginners is how do you actually get your code onto these boards and run them? When in the Arduino world, you have this nice little IDE, and there's even like the new Arduino Create IDE, like a web-based IDE. And so you go to that, you type in your code, you press upload, and it pushes out to the board, and everything's great. In the Micropython world, we don't have those IDEs yet. There's some that are out there. There's MU, the Micropython editor. That's a really nice one. Microbit focused right now, the BBC Microbit, so it doesn't work with a lot of the other boards, although actually it technically does work with Adafruit boards right now. We added support to it. But that's an editor that's out there, but it's still evolving, again, because Micropython is still pretty new. So the one cool thing that we've done, and you might have noticed, I dragged over, this is the Finder in OS 10, and you can see there's a Micropython drive, and this is, again, if you've seen our SAMD21 Micropython port, that's the cool thing about this processor is that it shows up as a USB storage device. It can look like a storage device, so you can drag and drop files to this board. And you can see I actually have a couple files on here already. I have a neopixel.py and a main.py file. Now I'm actually going to open this main.py file in a text editor. I'm just going to use a simple text editor. We'll use a text edit. And let me see if I can increase the font size because that's not going to help. There we go. All right, this will be a little bit large. So, put yourself in the shoes of like a student. You're in a classroom, you have this board, you plug it in, and now what? Because, most students probably don't know, oh, okay, I can use a text editor like, the Atom text editor or something. And even if you know how to do that, that's an extra step to install that. So just open it in the text editor that's on your computer. Okay, so I opened this file, and let's put some code in here. So I'm going to put in, this is CircuitPython code. So I'm going to use some of the newer APIs, and we'll just make the little pin 13 red LED on this board blink. So I'll show some of the code to do that. So first I need to import some modules. Like I mentioned, there's a board module that has all of our pins inside of it. So I'll import that. I'll import the native I/O module. That's the module that's like the machine module in Micropython, but it gives you access to all the hardware. So that's what I need to access digital inputs and outputs, because that little LED connected to pin 13 is a digital output. So if I set it high, it turns the LED on. If I set it low, it turns it off. And then I also want to have the time mod. Well, we'll come back to this. We'll just start with something simple here. So let's actually make an LED object. We're going to make a digital output. So in native I/O, there's a digital in-out object. And so this is an object that represents a pin that can be an input or an output. Because on most of your microprocessors, you have your GPIO pins, which you can control. You can say, I want this to be an input or this to be an output. So this kind of encapsulates that functionality. And you have to choose what pin that you're going to use here. And this is where the board module comes in. So you can say the board dot D13, so digital pin 13, which is what this LED is connected to, is what we're going to use. There are actually other pins you can use on here, and we're trying to make this a little bit simpler. So for example, there's a pin that's connected to the Neopixels, which drives them and sends a control signal to them. And you can actually access that as board.neopixel. So you don't need to know that, oh, that's pin 17 or whatever on this board. You know, we're going to put that as a nice little well-named object in the board module. For right now, you know, maybe we might add red LED later or something, an alias to it. But for now, you just have to know it's D13 for this. Again, this is beta stuff. We're evolving it. But let's make digital 13 an input or an output. And just to map this to Micropython, in the machine module, the pin class is what you might have used in the past to do digital inputs and outputs. So now it's native.io.digital_in_out is what you want to use. The next thing I want to do is I want to do led.switch_to_output. So by default, your digital in-outs start up as inputs, which is a safe state for most of your GPIO pins, because it basically means that nothing's connected, like the microcontroller is not driving that as an output high or low. It just acts as an input. It puts it into what's called a high impedance state, where the microcontroller is just letting the pin float at whatever value it naturally wants to go to, and it's just reading it. It's just looking to see, okay, what's happening, which doesn't affect the level of the pin. And that's important because if you had, like, let's say a relay hooked up to one of these pins, and then you created a digital input or a digital in-out object for it, if it automatically set it as an output and maybe even set the level explicitly, that might change your relay. You know, you might like turn something on and, you know, suddenly your robot goes zooming off in a direction you didn't expect. So in most cases, everything defaults to an input. And that's why right now we're explicitly saying switch to output. Now I'm doing this all using the native IO module. Oh, and I actually have a bug here. I want to say native IO, not native. But I'm using the native IO module. And like I said, you know, we want to make this beginner focused. So this is ultimately not the final way I'd say that we're going to show how to blink an LED. We're actually thinking about, is there an even simpler abstraction on top of native IO, like a simple IO module that has maybe a concept of an LED and a button, or, you know, an input or an output, or, you know, less code that you might need to write. But in a lot of cases, you know, once you get beyond that, for example, if you're like writing a driver to talk to hardware, you really want like this explicit control over, okay, I want this as an input or this is an output, and I need all this fancy extra behavior here. So again, this is going to evolve over time, but this is right now how you control a digital output. Okay, so now we've switched to an output, and then the led.value is a property. And so you can do two things with a property in Python. You can read it, so I can actually say, now we won't see any of this output, but I could print led.value if this was an input. It's switched to an output, so this won't work. But this is, for example, you could read, if this was an input, the current value of this would return a true or a false value if it's high or low. But the other thing about a property in Python is you can set it. So if I want to turn this LED on, I can set this to true. So led.value equals true. Okay, so let's see what happens. I'm going to save this file. Remember, I opened this file from Finder. It's on the board itself. So I'm just going to, let's go to File Save in the text editor here. So I click Save. And then, let's see, did nothing happen here? Demo fail. I did something wrong here. So, okay, let me reset the board, and we'll try this again. So I'm trying to show off, we have an auto reset functionality built into here, and I'll open up, actually, we'll debug this on the fly here. So let's connect to the serial REPL of this board. So this should be the USB modem, 115200. Okay, so I connected the serial REPL. This is where you type in your Python code typically. Now this is the cool thing. So it says auto soft reset is on. So you save your file on the USB drive to run it. So let's try this again. I probably actually have an error in my script, and that's why it didn't run. So let's open this up in our text editor again. And oh wow, it doesn't default the font to be big. Okay, so let's see if I got something wrong here. So I've imported native IO, and I created my LED. So yeah, this looks good. Let's just save this, and we should see that the board picks it up as a change. Okay, so I do have an invalid syntax here. main.py line 4. So you just saw a few things happen. I pressed Control S to save my text editor. It took a moment because the text editor has to save it, and then your computer has to push that change out to the USB drive. And then we saw in the serial REPL here the output of our script. So if you want to debug things, it could be useful. You can keep this open. Now you can see something failed. So line 4, invalid syntax. All right, so I must have done something wrong. So let's see, 1, 2, 3, 4. I probably have some white space in here that's bad. Let's see what's looking through. Let's just get rid of this. Oh, interesting. Looks like there's some white space that was there. Okay, let's try this again. Let's save this, and let's see what happens here. So I saved it, and it's still giving me that invalid syntax. That is a little bit funky what it's doing. So what is it mad about here? This is a little bit of live troubleshooting. Now, let's use another text editor. Let's use the fancy text editor just to make sure there's no crazy white space error here that we might be dealing with. So let's open up our board in this text editor. Okay, come on, Adam. Show us the open prompt. There we go. Okay, there's our board. Let's open the main.py in here. Here we go. Okay, interesting. So you can see it's doing something weird with the white space right here on this line. So let's delete all of this if it lets me. Wow, this is being a little bit funky. Okay, let's just save this and see what happens. Okay, there we go. So there's no output from our main.py. Now let's try this again. Let's go in and let's create that LED object. So native IO dot digital in out. And again, hey, this is why this is all beta stuff. So we want to kind of push this release out to work out lots of little kinks and things and find out what are some of the problems with some of the workflows. Okay, LED.switch to output. And I'm going to blame TextEdit. So, you know, I'm blaming the tool, although, you know, the people who aren't good, you know, if you're not really good at what you're doing, then you're blaming your tools. So I'm gonna make that same mistake. Anyways, let's try to set this to true again. Okay, now I'm gonna press Control S and save this, and let's see what happens. Okay, there we go. So you notice the red LED just turned on. So interesting. You know, we'll have to look more at some of these text editors and see. There are quirks. For example, on Windows, if you use Notepad, it handles line breaks in a different way than other operating systems. So you might see lines that run together. When in doubt, a proper programmer text editor is probably what you want to use, something like the Atom text editor or Emacs or Vim or VI or whatever. But you know, hopefully we want to be able to use some of these other text editors. So we'll have to see what some of the problems are with things like TextEdit. Anyway, so this is what I wanted to show in the first place is, as I change this code, as I save this file, the board's going to run it. So let's turn that LED off. I'm going to set the value to false. I'm going to just press, well, here, I'll go in the menu. We'll say File, Save, and then we'll see in a moment here. So you can see this is the REPL. It's outputting that it noticed that the file changed. It reset the board. You can even see it's telling you that it's doing that auto reset. It's actually going to print out your main.py output. So if I wanted, I could put, you know, let's just end it with hello world. So we can say hello world. I can save that again. And you see, you know, there's your output, hello world. So that's kind of cool. You know, I don't need to like use Ampy or a tool to run this script. I just save the file and it resets and it runs again. And you can see the LED turned off there. Now you might notice it says press any key to enter the REPL and disable auto reset. So I can do that. I'll just like press enter, for example. And now I'm at the Python REPL. So I can say, you know, hey, print hello world, and it'll do that. So the reason for this is that, you know, there might be cases where you want to use the REPL, like you want to go in and start experimenting with the APIs, maybe debugging things, and you might be editing files and saving them, and that could get really confusing if you save a file and then suddenly your REPL session just explodes. So we tried to look and see, okay, you know, when do we know is a user using the REPL, or are they actually just editing files and using this auto reset logic? So if you open the REPL and if you type anything, if you press any button, send any input to it, it will disable that auto reset logic. And it disables it only until the next time the board resets. So if I press Control D, as in dog, that does a reset of the board. And you can see it's back into that auto reset mode. So now I can save this file and, you know, we can turn the LED back on for this, and everything's all hunky-dory and working like we expected here. So that's one of the things I wanted to just show. It's a quick little demo of one of the ways we're trying to make this simpler for beginners, because like I said, there's a big learning curve in how you actually get your code to run on these boards. Like you, in the past, typically need to use an IDE like Arduino, and right now in Micropython, there isn't a really good IDE option that's ubiquitous and supports all these different boards. I bet we'll see one pretty soon though. But for now, there's not a clear way of how do I get my code to run on this thing. And even if there is a way to run code, if you have to use a tool like an IDE, you've got to download that tool. You've got to find it. You have to install it, which can be problematic if you're doing a classroom session, for example. You might not be able to install anything on those machines, and you might really only have Notepad or TextEdit on those machines. So this is cool in that it's just purely using the USB storage. Anything that can talk to a USB storage device and edit a text file, like Chromebooks can do it. Your Android phone might even be able to do it if you install, I'm sure, all kinds of file browsers and fancy apps, and have the USB on-the-go cables and all that fanciness. It should work in theory. It's just USB mass storage. So that's kind of cool. That could open up editing and running code to more devices and make it a little bit simpler for this. Okay, so that's one thing I wanted to show, and then real fast, I'll also show Neopixels on here. So, once we release the Circuit Playground version that has this SAMD21 processor and runs CircuitPython, then this will be really cool. We're going to have a library that gives you simple Python access to all the peripherals on your Circuit Playground board. And for now, we don't have that yet, but I'll just do some basic Neopixel stuff here. So let's just light up all the Neopixels on this board. So I'm going to import the Neopixel module, and I'll make a Neopixel object. And this is just like using the Neopixel class that you've seen in upstream Micropython that we've done before, but it is a little bit different in that, I don't have a pin object. I have my native IO digital in out object. And in this case, the board has a Neopixel pin already defined. So I just say, use your Neopixel input pin as the pin that is connected to these pixels. There are 10 Neopixels on this board. And then I'm just going to use the fill command, and let's just fill them with the red colors. This is to set all 10 of those pixels red. And then let's just do the neopixel.write to send that color out to the board. Now I'll Control S save it. We do that, and then hey, check that out. They all lit up red. And then if I want, I can change these to, maybe a green color instead of red. So we'll say, 0, we save it, and then there we go. They all light up green. So that's cool. And you can imagine in the future, we'll have a nice little, probably something like import circuit playground, maybe. And then on here, we'll probably have like circuit playground dot Neopixel 0 equals red or something like that. We haven't really defined this API yet, so more of this in the future, but it should be as easy as that to control the peripherals. It shouldn't have to be install all these modules and follow this long guide. And it could be even as simple as the board ships with that module included. You plug it into your computer and you just start running code that controls it directly. So no install at all. That will be really cool. So that's kind of where we're headed for in the future for some of this stuff. Okay, so I think we hit the highlights there of why we're kind of focusing on making things a little bit simpler. So we want to have a simple, easy workflow. And we want to simplify the APIs so that it's a little bit more catered towards beginners and people that might not know all the deep intricacies of the hardware and just want to turn a Neopixel a certain color. Okay, let's talk about and do a few demos of the consistency across the different boards of the API. So I'm going to switch to the ESP8266. This is the Feather Huzzah board. And I'm going to plug this one in, and actually let me go back. I just actually destroyed this terminal session on accident. If you have screen connected and then you disconnect your chip, the screen tool does not like that, and it like ruins your terminal session. So I'll open a new terminal here. Okay, I've connected my ESP8266. This is running CircuitPython. It's running the latest release of it. And so I can connect to the REPL on this. So we'll say dev.tty.scilabs USB to UART 115200 baud. And this is a Python prompt. And again, this has the exact same modules. So native IO is on here. The board module is on here. I can look at what's on the board module. And you can see this board module is much different than the board module that was on the Circuit Playground board. So you can see board pins on here, like GPIO 14, 4, your RX and TX for your serial inputs. Whereas on the Circuit Playground, we saw things like Neopixel, and there's left button and right button and other high-level pins on here. So again, that's the board module, just trying to show you exactly what's defined for the board that you're using, or for the firmware that you've loaded on this board, to make it a little bit simpler, so that you know on this board, this is really all of the pins that I have, and so that's all that I can control on here. Okay, so let me close out of here, because the other interesting thing, like I mentioned, we wanted to have a uniform API that you can use across multiple boards here. So if you take a look at our GitHub repository, and I'll put a link in the description below, search for CircuitPython, and you'll see a lot of repositories that are Adafruit _CircuitPython_ something, like a hardware name. And so these are drivers that we're porting over to work with the CircuitPython API. And we're basically we have Micropython API, machine API compatible versions of these drivers that we wrote last year. And so we're porting those over to work with CircuitPython. And it's actually not that big of a port. And I'm going to do more videos in the future to show how to do that, because the differences really aren't that great between these. So these are the CircuitPython specific versions, and I'll show you just a quick little demo of this HT16K33. That's the driver for this LED matrix. And I'll show how to load this up on the ESP8266. And the cool thing is, this code would be exactly the same if I had this and used it with maybe a Metro board that's using the SAMD21 microprocessor. And I don't have my Feather handy. Well, actually I do. Let me pull this open. So for example, this is a Feather M0 ADA logger, so it has the SAMD21 microprocessor, and so the same code could run on CircuitPython on this board, on the ESP8266 board. The same code will run to use that driver. Now I'll show real fast how to use the CircuitPython drivers, and again, this is a moving target. Not all the drivers have been ported. We're kind of in the process of doing that. The guides haven't been updated yet to call out how to use these drivers with CircuitPython, so expect to see in the next few weeks a lot more updates and more info about that. But anyways, this CircuitPython driver, this HT16K33, just like our other Micropython drivers, the release tab is where you want to go to get the release of this. But now you'll see that the drivers come as a zip file. And so you download this zip file, and then let me open up the Finder here. Whoops, uh-oh, come on, let's go here. And let me just grab real fast in the downloads an example of this thing. So yeah, so here's that HT16K33. So you open the zip file up, and you'll actually find a folder called HT16K33, and inside of it will be a bunch of .mpy files and this init.py file. So this is different from the Micropython drivers we had before, where we distributed just these pure .mpy files, and you had to copy these onto your board and then start using them. Now we're actually distributing a Python module, which is a folder, or a package actually is what it's called, which is a folder that contains a bunch of sub-files, which it actually contains these files inside of it. And so the nice thing is, you just have to copy that folder onto your board. You don't have to copy all the individual folder files. I mean, you do have to copy them because they're inside of that folder, but it structures things in a better way, so that in Python you can have a complex module with a lot of source files, but it just looks like one module. You import the Adafruit _HT16K33 module, and then you get access to everything inside of it. So you'll see that a lot with our drivers for CircuitPython going forward, in that they're going to use these Python packages, and you'll get a zip file like this 16K33 file right here. So look for that, and I'll show real quick how to use this. So you need this HT16K33 zip file, and then you also need two other modules to use this. So you need the CircuitPython bus device module. So this is, again, in the release tab, grab the zip file and you'll find a bus device directory. And then there's also a register directory or a module that you need. And so look in the release tab and you'll find this register one. So these are just abstractions that help us write drivers that work across different boards. So we're basically looking at, because all of these devices, like this little HTK chip, it just has a bunch of registers. So there's a register that controls which LEDs are turned on and which ones are turned off, and if it's blinking, or what's the intensity of the light, and things like that. And so we've taken some higher level abstractions to look at how we can simplify the drivers and just operate on those registers at a register level. So the previous drivers that we had were more at an operation level of, I need to make an I2C transaction to set this register to this value. Which is fine. That's perfectly okay to do that. But your code is a little harder to read because, if you're looking at the code to maybe blink this display, it just needs to change the blink register. But you see all of these different I2C calls and transactions and things happening. So it's a little bit confusing, whereas we're trying to take an approach to say, well, let's just model that register as an object in Python. And so if you actually look at the code for this HDK driver, you can dig into this, and I'm going to do some future videos on this. This is an advanced topic, but you can see we start to model some of these things as this is maybe a bad example. Let's go to a different driver. So that driver doesn't actually use that abstraction, but let's look at let's see. How about one of these real-time clocks here? So let's go in and see. And I haven't actually looked at this code, so I might not be finding the right thing here. But yeah, here we go. This one has an example, it looks like. Yeah, so there's a property here, this date time register. And basically, this lets you deal with a date register without having to use these low-level abstractions. I'm going to do more videos in the future to go into how to write a driver and why that's interesting. But again, so this is a big difference with CircuitPython and with the drivers we have for it. Most of them are going to require this bus device and register library to be on your board. Now, eventually, once we start shipping these boards with CircuitPython loaded on it already, we'll probably include these modules on the board itself so that you don't necessarily have to have them out of the box. And we're actually working on maybe some tools and things to bundle all of our libraries together so that you buy your Metro board and it comes with the current version of all of the drivers on it so that you don't even have to install anything. But that's for the future. We'll come back to that later. Anyways, let's get back to a demo here. So I have my board connected, my ESP8266 board. Now for the ESP8266, it does not have a mass storage mode, so I can't plug it in. I can't access it from the OS X Finder. So I need to use a tool like the AMPI tool that I've used in the past to copy files over to the board. So I'm going to use AMPI, and I've done videos on this tool, so I'll link to those videos in the description below, and you can see, and actually I have a whole guide on it that talks about this tool. But it's a tool that you can use to copy files in between your board. And so I can say AMPI, I need to point it at the serial port for my board, so the Scilab's USB to UART, and I can just run this ls command. This will list the files that are on the board. So you can see there's only a boot.py file on this board. And I'm going to do one quick little thing. I'm going to export the AMPI port. I'm going to set an environment variable to this dev tty.scilab's USB to UART. So now I don't need to specify this port parameter. I can just run AMPI ls, and it picks up that port from this environment variable that's been set. Okay, so now I need to copy over, and in this directory I have actually those files that I downloaded. So I have that Adafruit bus device folder, and if I go inside of here, if I go into the bus device directory, you can see this has those .mpy files and this init.py, so these are some sub files. Now I need to get these onto the board, and I actually just made some updates to the AMPI tool earlier in the week that it can recursively copy a folder from your local computer onto your board. So this is super handy for copying over these modules. Because in the past with AMPI, it only supported a single file at a time, and so you would have had to first create the directory and then copy file by file, which that doesn't cut it when we're wanting you to copy a lot of folders and things over. So make sure to upgrade AMPI if you haven't yet. You can do basically like sudo pip install Adafruit-AMPI, and then add this magic -- upgrade to the end. I don't know why. It's one pain point I have with pip is that, if you don't use this upgrade and you already have it installed and there's a newer version, it won't pick the newer version. It'll just keep the version you have installed and it won't upgrade it, which seems a little weird to me. It seems like it should just default, it should tell you, by the way, do you want to upgrade? But anyways, that's a rant for another day. So make sure to add this upgrade, and then you run this and it's going to go and upgrade things, and it's probably going to complain that I'm running this as sudo. That's just because on this machine I have like multiple versions of Python installed. It's a mess. But on some machines you have to use sudo, on other machines you don't. If you're using homebrew, you don't have to use sudo when you run pip. Anyways, you can notice I already have the latest version of AMPI, but upgrade AMPI, and you'll notice if you run help with AMPI, you should notice there's a new command that we're going to look at in a second, this rmdir. If you don't see rmdir, then you're using an older version. But now the put command actually supports a file or a folder now on the board, and it works really easily. So, you know, locally in this directory, I have an Adafruit register subdirectory. So I can say ampy put Adafruit underscore register. So it's going to pick this Adafruit register folder from my local machine. It's going to copy it directly over to the root of the file system on this board. And all of the subfiles inside of there, all of the subdirectories and all of the subfiles inside of there, everything, it's going to copy it all over. So I'm going to run this command. It takes a little bit of time because it's got to send that whole file over the serial connection here. And this is really handy though, so that it, just one little command, I can copy a library over to the board. So now if I run ampy ls, you can see there's an Adafruit register directory here, and I can actually look ampy ls Adafruit register. So this will show me what's inside of that folder. And you can see, yeah, we see here's all these .mpy files and that .py file. So everything copied over that I expected. So that's cool. Now let's put the Adafruit underscore bus device module. Like I mentioned before, this is another dependency of our CircuitPython driver for the HTK display. Okay, so that was copied over. And then finally, let's put the Adafruit underscore HT16K33 module. So that's the driver code that talks to this little matrix display. So we'll copy that over. And okay, so now I'm going to plug in my matrix display to the feather. So that's just this is the 16:8 matrix, LED matrix feather wing. So I just plug that in. And now, okay, so if I run ampy ls, I'm just going to list all the files that are on the board. So cool, so we've got our directories there. And then there is an example file that I think I have in this directory. Yeah, so there's this matrix.py file, and I'll just show you real quickly the source code for this. So matrix.py, and this is basically just a quick little demo that shows how to use this matrix display. So you can see it's using the board module. We're importing all of the pins right here, and then we're using this bitbang IO module to get our I2C interface. And that's because on the ESP8266, it only supports bitbang software I2C. But you could just swap it out, this native IO module right here. So I can import native IO if I uncomment this. And so if I'm running on like a SAMD21 or another microprocessor that has native support for this, for I2C, it's easy to swap it over. And I'm just using a little Python syntax thing where you can import a module that has a name like bitbang IO, and I can change the name I imported as by adding this as IO. So that way I can just swap, my code below is just written to use io.I2C, and then if I want to switch between bitbang IO or native IO, I just comment or uncomment which line and how I alias that module when I import it here. So you'll see this a lot in the examples that we have. But anyways, so I create the I2C interface. This is really nice in that I'm just passing in this SCL pin and this SDA pin. This is coming from this from board import star module import line right here. So I have an STL object, an SDA object that I can pass in to make this really simple. And then the rest of this code is exactly the same as the old driver. I create an instance of my matrix class, I pass in this I2C interface that was created ahead of time, and then I can just call some functions. So in this example code, it's just going to turn all the pixels off. So I use the fill0 command and then show, and then I just turn on the top left, the middle, and the bottom right pixel. So I just kind of show the extremes of the pixels. I just turn those on using this matrix.pixel command and then matrix.show to show it. So okay, let's run this. I'm going to use the ampy tool. Let's run matrix.py. And hey, check that out. So we just lit up, you know, there's your top left, middle, and bottom LED. They were just turned on from the code that we ran. So, you know, you can go back and look at the code and see here's what's happening for it. So you can see, you know, pixel 00, the middle one, 84, and then 15.7, they turned on. So it's as easy as that. You know, you basically, I copied over the libraries. On the ESP8266, I had to use the ampy tool, which now has the fancy recursive copy, whereas on a SAMD21 board, I could just use the Explorer or the Finder tool and just drag and drop those folders over to the board. And so it's as easy as just getting those folders onto the board and then running the code that interacts with it. So again, that's one of the focuses that we have with CircuitPython, is that we want these APIs to be the same across boards like the ESP8266, the SAMD21, and who knows whatever future boards are going to come out. Well, there's already the ESP32, which hopefully in the future I might do a video on that. But you know, that's probably going to be an interesting chip to check out this year. I'm sure there's going to be a whole slew of new processors. By this time next year, we'll probably have moved on to the next latest and greatest processor. But again, because we're going to keep a consistent API with CircuitPython, it'll be nice in that as we have new boards from Adafruit that use different chips, we'll implement the same API, and that we'll be able to use the same code across all of these different boards, or using with very little modifications your code across there. And who knows? I mean, eventually, hopefully, the upstream Micropython boards also solidify and get a consistent API, because that'll really help with getting lots of code and things to run across different boards. But it's a little bit hard because each board sometimes has different priorities. Again, some of the boards are focused more on giving very low level, complete access to the hardware, in contrast to other boards that might be simpler and just trying to give you a easier access to the hardware, or something that's less complete, but maybe less verbose in some cases. So, okay, I'm gonna wrap up this video then. The last thing I will mention, and I'm just gonna mention this, and I'll put links in the description when this goes up on YouTube. So you're probably wondering, what now? How do I check out CircuitPython? Like I said, go back to this blog post that I'll link to, and this has links to the API documentation, the firmware, which is on our GitHub repository. So you can find this under the releases of the GitHub repository. So you can grab these .bin files, you load them onto your board using the previous guides, using tools like the ESP tool for the ESP8266, or the Bossa C tool for the SAMD21. You load on your board, and then you can see there are links to the documentation, so you can start to play with the hardware APIs. For all the drivers, like I said, we're in process of porting some of these over, so I'll have some links to the GitHub repositories. But as we port things over, we'll post to the blog updates, and we're also going to update the Learn System guides, so you'll see more info there. So definitely check out the blog, the learning system, learn.adafruit.com/category/micropython. That's where all of the learn guides for MicroPython will go. So we'll see updates to there. There's also the forums. So at the Adafruit forums, you can check out, there's a MicroPython forum. So it's good to ask questions. If you're using MicroPython or CircuitPython, ask your questions in that forum. If you're troubleshooting stuff, use the forums there. If you're working on the CircuitPython code or MicroPython code or the drivers and things, GitHub is probably the better place to interact with it. So, don't take your troubleshooting questions to GitHub, for example. Like if you are trying to use CircuitPython and you're getting an error that you don't know what it means, go to the forums first, because there are more people that'll see that. Whereas if you post that on GitHub, GitHub is really for investigating like problems with the code or issues. If you find a bug, then raise it on GitHub, and we can discuss it and figure out how to repro it and deal with it. So just try to work to not clutter the GitHub repository with a lot of noise or issues that might be better solved by a forum question or support follow there. So check that out. And then there's also something called Gitter, Gitter, which is basically like Slack or HipChat, but integrated with GitHub. And so there's a Gitter channel for CircuitPython, and I'll put a link in the description when this goes up on YouTube, so you can check that out. That's again good if you're working on the CircuitPython code and you have questions about the code, or maybe trying to look at how to use it, or how to modify the code. Don't take your troubleshooting questions there though, again, because GitHub and Gitter is for problems with the code and working on the code. Forums are for troubleshooting and support. So when you don't know what's wrong, that's troubleshooting. So that's kind of I've reached the limits of my knowledge. I need some more help from someone. Take that to the forum. When you know what's wrong, when you've realized, hey, you've got a bug, you didn't interact with this hardware the right way, take that to GitHub, because then that'll get to the right people, the right audience there. So anyways, I'll put links to all this info, and stay tuned. So like I said, this is going to be a whole year of all kinds of fun CircuitPython and other fun MicroPython related things from Adafruit. And like I said, you'll see a lot more of these boards. Right now we got some prototypes, but keep your eyes peeled. You'll see great stuff in the future coming from that. So we'll jump back to the main view, and if there are questions, maybe throw them into the chat, but I'll wrap this up because we're running about an hour long. So I wanted to make this kind of a quick video to just serve as an introduction to CircuitPython. So I don't see a lot of questions. So yeah, I think I'll wrap this up then. So thanks a lot for watching. This is Tony from Adafruit. Check out youtube.com/Adafruit. You can see this video and all kinds of other fun project videos. Check out twitch.tv/Adafruit. That's where I stream these things live. In the past, last year, I did a bunch of live streams. I think almost 100, around 80 or so. I did a lot. This year, I'm going to do live streams at least every Friday. We're doing a lot of other new live shows potentially, so keep your eyes peeled. But to make room for those, I think for now I'm just going to do one live stream a week on Fridays, probably around this time in the evening Pacific time. So check that out. For the next few weeks, I think I'm going to be focusing on CircuitPython and just diving into some of the usage. I'm probably going to start with more advanced videos in the near future of things like porting over drivers, just because that's kind of what we're doing right now. But as we start to get some of the hardware finalized and some of these things like your Circuit Playground that runs CircuitPython, and as we start to have some of the simple APIs and things, expect to see a lot of cool content and more videos and things of that nature in the future. So until next time, I'll see you guys later. So Tony from Adafruit, thanks for watching. See ya.